You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you. Hello, this is Richard Jacobs with the Future Tech Podcast. I have Jorge Vago. He's the project scientist for the ExoMars Rover, recently named the Rosalind Franklin. He's part of ESA, the European Space Agency, and ESA is very gracious. They've, Erica Verberlin at ESA has had me speak to probably at least 10 of their scientists already. So she's great. They're great, and I always enjoy talking to them. So Jorge, thank you for coming.
Thank you.
Yeah. So tell me about the ExoMars Rover. When will the rover be scheduled to go to Mars, and what will be the mission of the rover?
Okay. So the launch opportunity for this mission opens on the 26th of July 2020 and closes on the 11th of August. And no matter when we launch during that period, the landing will take place on the 19th of March 2021.
Yeah, I have a quick question about, can you talk a little bit about launch windows? Why is there a window, and what happens if you're outside the window?
Okay, so the people that compute trajectories for getting between planets try to come up with strategies that allow us to get to where we want to go with the rockets that we have. In this case, we're using a Proton M, which is one of the most powerful rockets that Russia has at its disposal. And we have trajectories to go to Mars every 26 months, give or take. And there is a period where the rocket has enough oomph to get you there. This is what we call the launch window. If you launch before or if you launch after the launch window, then you need more energy than what the rocket can provide.
And why is that? Is it because the Earth is just not at the right trajectory, and the path to Mars is longer, or is it is there more resistance somehow?
Now, the reason why this is so is that Earth and Mars have different orbital velocities for going around the Sun. There are times when you have Earth on one side of the Sun and Mars on the opposite side of the Sun, and you can imagine that that's the furthest away you can be one from the other. There are other times when they are both on the same side of the Sun and more or less directly on one line, and that can be considered the closest they can be. But that's not when you want to launch. You want to launch at a time when Earth is about to catch up with Mars. And since it takes in the order of 9 months to get there, you want to time things just right so that Earth is catching up on Mars and you launch just before. So by the time your rocket gets sufficiently far out, it just happens to encounter Mars when it gets at the right distance from the Sun. So that
makes sense.
A cosmic alignment happens every 26 months.
Okay, that makes sense. I spoke to someone about Mercury, and they said that takes like 7 years because of all the slowdowns that have to happen in order to get there.
It's great that you know that it's slowdowns. When you go out further away from the Sun, you have to accelerate. When you want to go closer to the Sun, you actually have to brake.
Is all that due to the Sun's gravity?
Oh, it's due to the fact that the Earth and you on it are going too fast in order to fall to, let's say, an orbit that is closer to the sun. It's the same thing that happens when astronauts want to go to the space station. They accelerate in order to be able to get out of Earth and get to an orbit. If you want to go to a higher orbit, you need to accelerate even more. And if you want to descend, you need to brake.
Okay, gotcha. So how long is a Martian year, in the amount of time it takes for it to go around the sun versus us?
Martian year is 668 Mars days, which are slightly longer than Earth days, by about half an hour. A bit more closer to 40 minutes than half an hour.
Okay, so the Mars year is, close about double our year.
About, yes. And the further you go out from the sun, the longer the year of the corresponding planet will be.
Okay. And just for a frame of reference, how long is the year on, Jupiter and, let's say, Uranus and some of the other planets?
I have no clue. But it's several,
but longer.
Much longer than the Martian year. I'm not sure.
Okay, no problem. All right, so back to the Mars rover, the EXO rover. What's the point of this mission? What's special about this rover?
Two things. First of all is the fact that we want to target the possibility that life may have existed on Mars in its infancy. So let's say 4 billion years ago. And hence, to be able to do that, we need to land in a place where the deposits that we will study are from that era. And no mission has gone that far back in time on Mars yet. So we will land by a good 500 million years on terrains that are older than anything that has been visited on Mars or Earth, for that matter, before. That's point number one, the trip back in time. The second thing is that because Mars has a very tenuous atmosphere and then cosmic radiation penetrates more or less unimpeded and slams the surface, degrading and eventually destroying the biosignatures that we would like to study, we have implemented a strategy that is pretty novel to try to secure samples in a very good state of conservation. And what we do is we look for those samples in the subsurface, relatively deep. The deepest that any mission has dug on Mars so far is in the order of 5 to 10 centimeters. We will be equipped for the first time with a drill able to penetrate 2 meters into the subsurface. So the idea is that you use all the material above the place where you will collect the samples from as sort of a shield against the ravages of cosmic radiation. We will see if that allows us to find the biosignatures we are seeking, if there was life on Mars, of course.
Is there any part of Mars that has been building up over time where layers are being deposited over what was there, or is it all being abraded away and exposing new layers?
Well, the place we're going to, which is called Oxyaplanum, a bit like what you just described. The deposits we're interested in, we know they were laying down in the order of 4.1 billion years ago, but indeed, afterwards they were covered by newer, more modern deposits. For example, there was a delta there about 3.9 billion years ago that covered most of the area, and then about 2.5 billion years ago there was some sort of an eruption close by, probably several, and there was this lava or pyroclastic-like deposits that covered the entire area. But all of that, or most of that, has been eroded away by wind in the last 500 million years or so. So this is good for us because it means that the deepest deposits, the ones that we are most interested in exploring, have been covered and therefore preserved from ionizing radiation damage for a good 3 billion years. And it's only relatively recently that they have been exhumed by the action of wind erosion and brought up to the surface again where we can study them.
Oh, okay. I gotcha. Are there parts of Mars that we won't be able to get to for a long time that are because they're for some reason they're just opposite to where we're able to land? Like what percentage of Mars are we able to land on, and are there inaccessible parts?
There are parts that are inaccessible to the technologies we have today. And those are the bits of Mars that are too high for our landing systems. So if you look at Mars, you will see that most of the southern hemisphere has a very high elevation, and most of the northern hemisphere has a much lower elevation. And the difference in height is in the order of 6 kilometers, more or less, which is a lot. Because presently we use initially the heat shield during the hypersonic part of the entry. So when you're going from roughly 20 times the speed of sound to supersonic speed. But thereafter, we need to deploy parachutes. And those parachutes, they need sufficient atmospheric bite in order to slow us down for us to be able to use rocket engines for the latter part of the descent. That is a limiting factor. That's how much atmosphere we need for the parachutes to work. So, for example, if you wanted to land at the top of Olympus Mons, which is the highest volcano on the solar system, it has an elevation of more than 20 kilometers with respect to the ground. In fact, the tip actually sticks out from the atmosphere. Well, you wouldn't be able to go there because your parachutes wouldn't work. So the landing sites that we can choose from today have to be at a low enough elevation for parachutes to work. And typically this precludes most of the southern hemisphere.
Okay, very interesting. How old is Mars relative to Earth? Is it about the same age, or is there a big difference?
No, it's the same age. There is one difference though. The planet is the same age, but the surface is not. And the reason is that Earth has plate tectonics, which allow, continental masses to move about, and big parts of Earth's crust get recycled. They go under and get recycled in the mantle. They get recooked to relatively high temperatures, and so it's very difficult for us on Earth to have access to rocks, let alone large expanse of land that are older than 3.5 billion years in age. In fact, there are only very small bits of Earth that are that age. Whereas on Mars, because it's a much smaller planet and it had a different cooling regime, we don't think it ever had plate tectonics. Basically, the whole crust behaves as just one single lid. And so the terrains are, if they were not covered by more modern terrains, if you can get access to the old stuff, are as they were when they were deposited. And so there are parts of Mars which are 4.1, 4.2 billion years in age that we can get to. So if you like, we can study rocks of an age that do not exist any longer on our planet.
Oh, wow. And that would tell us a lot about the early formation of our solar system, right?
Indeed. I don't know if they would tell us much about some of the larger planets because they're totally different. But when it comes to Earth, Venus, and Mars, I think they shared very similar early stages of formation and evolution. And hence, we will be able to, for the first time, access this age of the baby or toddler planet. So,
okay.
For example, one thing that is interesting, this interaction between rocks and water and prebiotic compounds that may have eventually led to the first proto-organisms on Earth. That we cannot study anymore. If there was life on Mars at the landing site we will explore, we will be able to maybe make some important steps in trying to understand what it is that needs to happen for chemistry to make that important step from blocks to actually a functioning system that we may call a very early organism, for example.
Right. So how deep would we have to to drill on Mars so that we could drill anywhere and still get the oldest rocks and the oldest material?
I thought you were going to ask me how deep we would have to drill to find living organisms today.
I don't. Yeah, if they exist, or that too.
Yeah.
I mean, I guess both questions then. Yeah.
Well, the first question is risky in the sense that I would rather land on a place where I can see we have the old rocks. And the way you know that you have the old rocks is you count how many craters they have. Because if they have been exposed for a while and if they're indeed old, then the crater population tells you about the age. But
because in the early solar system, there was a lot more bombardment of Mars and Earth and all the planets by meteors?
Well, it is a bit complicated because there is bombardment all the time. There is bombardment even now. Of course, the rate of meteoritic bombardment we have now is not very high. There was a lot more bombardment in the beginning, but also in the beginning the atmosphere was denser, which would have shielded the surface from, let's say, the smaller type of meteorites. But yes, you can determine the age of the surface by counting how many medium and large craters you have. The smaller ones are trickier.
Okay, gotcha.
For the second question regarding the possibility of finding life on Mars today, we think that it is impossible to have metabolizing organisms close to the surface, mainly because they wouldn't have any access to liquid water. If you want to have liquid water that organisms can use, then you would need sufficient pressure for liquid water to be possible. And for that, you would need in the order of 1.5 kilometers of rocks on top of you. So you would need to drill 1.5 to 2 kilometers to have a chance to find liquid water and hence possibly organisms living off that liquid water, which we see on Earth. If you search for oil and you drill deep, you will still find microorganisms that live off differences in the valencies of metals, the munch chemistry.
With water, or just, how would the metals migrate towards the organisms or away, if not by water?
Well, the water is needed to create various things that are required for a cell to function, including the cytoplasm, which is liquid, and various other substances and organelles. But no, the metals are part of the rocks. For example, if you have silicates, some will have iron, others will have magnesium, and the organisms will use the metals they need from the rocks. They don't need to move too much necessarily. If they have what they need, an organism that has a size of 10 microns, finds a cubic millimeter, a wonderful universe to live in, provided it has what it needs to exist. Okay,
I gotcha. Right. So it doesn't sound like we're going to be able to look for evidence of life on Mars anytime soon, because drilling down a whole kilometer seems to be a major task.
Indeed, but maybe we have a chance to indirectly infer the presence of active life. If you like, that is what we were trying to do with the Trace Gas Orbiter, the ExoMars 2016 mission that works like a big nose in the sky, trying to analyze trace gases that exist in minute proportions in the Mars atmosphere and see if we can detect something that would be suggestive of metabolizing archaea or bacteria present somewhere.
Okay. So it's going to arrive in March of 2020, and then it's going to set up and prepare and drill. And how long will it take to drill down? You said 2 meters it's going to drill down?
Yes, 2 meters. We think it will take us in the order of 5 to 6 days to get to that depth. And I don't think we're going to do it anytime soon after landing. We will proceed in a very cautious manner So I expect it will take us a good 10 days to 2 weeks possibly to get off the landing platform, and then we will have to move away from the blast area, from the descent engines, because that produces ammonia, and ammonia is an interesting substance that could be considered a biomarker of sorts. So we want to be sure that if we detect ammonia, it's not from the engines. So we would move away a good 50 to 100 meters from the landing site before opening the analytical laboratory in the rover, and then proceed carefully with the drilling. I would expect that we would first get samples from the surface, try to understand the geology, and then it would take months before we would commit to drilling deep. You really want to understand the system and how to use your rover in the best way possible before you commit to more risky operations.
Are we planning to drill just once, or are we going to try to drill multiple times?
No, we expect that during the first 7 months of the mission, what we call the nominal mission, we should collect and analyze in the order of 20 samples, of which I would expect half would be from the subsurface.
When you start drilling, what would you do with the gases that would be volatilized from the drilling itself, especially when you get close to the depth you want?
We love those because they help us to remove the fines from the borehole. So indeed, if there is a bit of water, for example, aggregated around mineral grains, if that water gets warmed up by the drill tip as we are drilling, it will produce sort of I would call it an exhalation that helps to move fines or the drilling powder out of the hole. The drill has what is called an auger. An auger, it's like a helicoidal strip of metal that snakes around the drill, and while you're drilling, this auger collects the dust and brings it out of the hole. And this is very important because you want your drill tip to actually be fracturing material. If you are not able to get the fines or the powder out of the hole, all you will be doing would be just shaking the powder around, and you wouldn't be able to make any downward progress. So getting these fines out of the hole is super important for having good drill operations. So this bit of volatilization that you were talking about gives a hand to the auger in getting the fines shot out.
And I guess maybe the auger acts as like a helical elevator for the material. As it spins, it I guess elevators the material out of the hole and maybe radially out to the sides of it on the surface.
Exactly. A great way to explain it.
Okay. And then the processing of the material is going to be done on Mars using the rover's lab, or is any going to be taken back to Earth later?
No, unfortunately, this is not a Mars sample return mission. So indeed, we're going to collect the sample with a drill, pass it on to the analytical laboratory, crush it, and analyze it inside the rover. We have 3 instruments for doing this inside the rover. We have 2 spectrometers for doing mineralogy, and one, the biggest, the most complex instrument we have in the payload, which is devoted to the analysis of organic substances.
Okay. So what are we hoping to learn as a recap from the drilling and the sampling? What possible things do you think could be found?
Well, the first thing is we would like to understand how things vary with depth. This is the first time that we will analyze Mars's third dimension. So things like these pesky oxidants that have plagued the observations of previous missions like Phoenix, Viking, and Curiosity that degrade organics. Are they more prevalent close to the surface? How does their distribution and activity change with depth? The other thing is, by going down into the subsurface, hopefully we will be able to prove this hypothesis that material is protected from ionizing radiation when it's in the subsurface. And so we are pretty sure we're going to find organic molecules because they have been found also by curiosity close to the surface. But most probably those organic molecules have a meteoritic origin. So they came with fine meteorite powder and have nothing to do with life. So we will probably have to deal with these cosmic organics as some sort of a background from which we want to disentangle the possible existence or presence of true biosignatures, if they do exist. So these biosignatures, which would be the residues of molecules that would have existed in living cells, those we would like to be able to identify and analyze. So that's if you like, something that we are trying to do in a new way. Because we know that there are oxidants on Mars, and we know that those oxidants have made the life of previous missions very difficult when it comes to the analysis of organics, we have a new method of extracting organic molecules that works without activating these oxidants, these perchlorates. So the MoMA instrument on the ExoMars Rover can extract organic molecules in the same manner as Phoenix, Viking, or Curiosity, using small ovens that get heated up and therefore release organics. But it also has a new way of extracting organics, which is by using a UV laser and doing what is called laser desorption mass spectrometry. So this UV laser zaps the sample with a very high energy pulse of light and gets the organic molecules to become volatile, sort of like a gas, produces ions that are separate from the sample and then are ingested into the mass spectrometer that is able then to tell you which compounds you have.
Okay. Well, very good. So you're anticipating within maybe by July or October of 2020 that the rover will have landed in March and then samples will have been processed?
Yes, we will have analyzed a few samples if all goes well by then, but don't expect any news. I mean, maybe we will tell you that we found organics, but we're going to be super, super cautious about making any pronouncements as to the possible biological origin of any of the organics that we may find. First of all, because you want to be sure you don't make any announcement that may thereafter be proven wrong. Secondly, because the analysis of the organic molecules, even with an instrument like MoMA, is going to be difficult. As I mentioned, you need to be able to separate what may be cosmic organics and therefore not biological from other signals that you may find. And a lot will depend on what is the status of preservation of the candidate biosignatures, if they exist. If you find, well, let me give you a hypothetical or a thought experiment. If we were to drill into soil that contains living organisms today, which I want to clarify will not be the case, because I don't think there will be living organisms anywhere close to the depth that we can access. But let's assume for a second that there could be living organisms. Then our payload would detect them very easily. Why? Because in that case, you would have access to the Lego building blocks of cells that are more or less alive, which means, for example, that you would find very well-preserved phospholipids, which are the elements of the cell membranes. You would find amino acids, which are present in most of, they're very prevalent in proteins, everywhere in the cytoplasm of the cell. So all of these would be ringing like alarm bells in the instrument. That will not be the case. So what
Right.
is it that we expect to find? Most probably, it will be the degraded remnants of those mother molecules. And unfortunately, they don't all survive equally well in the geologic record. So after a cell dies and its organic constituents are released into the environment, amino acids are relatively quickly destroyed. On Earth, for sure, because other life will eat them up and water will degrade them. They don't like high temperature either. They're relatively fragile compounds, which constitute something like 80% of the organic molecules you have in a cell. Phospholipids, the ones I mentioned from the membranes, they last a long time. They're very hardy molecules, but they only constitute like 1.7% of the organic molecules on a cell. Some things help you on Mars. For example, the fact that it's very cold. Once you dig in the order of 1 meter into the subsurface, the temperature is the average between day and night, which is something like minus 60 degrees. So it's like putting your compounds in a freezer, which is a great thing. But I told you about ionizing radiation. That doesn't help. So we don't know. We will have to see to what extent going into the subsurface helps you to find these remnants of possible life in such a state that the instrument and the scientists are able to tell they're there.
Okay. Well, very good. We're just about out of time, but this is it's going to be a big mission, a big experiment, and hopefully that at least the remnants of life will be found. And here's a question: so, what will you interpret if nothing is found versus substantial or evidence of past organic life is found? What will that tell you, either scenario?
Well, the most probable scenario is the one you haven't mentioned, which is that we may find something that is suggestive that maybe there could have been life, but we are not 100% sure. And that opens up the door for what many people think should be the next mission, which is go and collect the most promising samples and bring them back to Earth for analysis. That's what NASA and ESA are working on as the next mission to undertake together, Mars sample return. I think maybe if we get super lucky, we would be able to demonstrate that there was life on Mars. But it really would require being very, very, very lucky. I think the scientific community on Earth is naturally skeptical. If you want to make such an important pronouncement, you really, really, really have to be sure. And in order to be sure, you need to amass a very compelling set of evidence. And that would require ticking many, many boxes in terms of biosignatures. Mind you, we are trying to put ourselves in the best possible position. And so we have come up as a mission with what we call the ExoMars biosignature score. So we have identified the biosignatures we think we could explore for and assign scores to those. And then we have set up, if you like, a minimum level or a minimum score before you can claim that you think you have found traces of life. Of course, we wanted to see whether that made much sense, so we have applied that scoring system to a number of Earth and Mars detections. And I can tell you, in most cases, we come out with a tail between our legs. We cannot demonstrate we have found traces of life even on samples that we know have traces of life. So it's not easy with a robotic mission using instruments far away to achieve the same level of scrutiny that you can have when you have your samples in a university on Earth and you can apply the best possible techniques we have access to on our planet. So, I mean, even if we have done the best we can in terms of putting together a great payload for a great rover mission, we still need to accept we have to be humble about the discoveries we will be able to make on Mars.
Okay. Well, very good. Understood. So where's the best way for listeners to find out more about the EXO rover and to track its progress?
Well, at the moment, you can look at our exploration website at exploration.esa.int. That you will find a lot of info on the ExoMars Rover, the instruments, and what we are trying to do. Once the mission will have landed, we intend to have a daily journal of rover activities accessible to the public. And there we will tell you on a map where we are, where we plan to go, what it is that we are planning to observe on that day and the day after. You will be able to get images every day, and we will give a bit of an idea of what it is that we are experiencing. Then for the big findings, that you will have to wait until the data will have been analyzed, processed, scrutinized by the team, and then the papers will have been written. And hopefully for big discoveries, we will have press conferences where everybody will be able to take part on the big announcement.
All right. Well, very good. Well, Jorge, thanks for coming on the podcast and giving tons of detail and information. It's been good to talk to you.
Okay. Thank you very much, Richard.
You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you.